everyone, I am Sahana, presently studying in Sri Venkateshwara College of Engineering, Department of Information Science and Engineering, and today in this video I'll be talking about properties of groups and subgroups, and let's begin the topic. Introduction to groups and subgroups. A group is a set G with a binary operation that satisfy closure, associative, identity, and inverses. Subgroups are subsets of a group that form a group under the same operation. Subgroups inherit properties of the parent group such as closure and associative. The definition of subgroups and groups. A group is a set G with a binary operation star written G comma star such that the operation star is closed and well defined on G. The operation star is associative on G. There is an element E belongs to G such that G into E equals to G and E into G for all G belongs to capital G. The element E is called the identity. In particular, G is non-empty. For each element G belongs to capital G, there is an element H belongs to capital G such that small g into H equals to E equals to H into G. This element H is called the inverse of small g and is often written as G inverse, and this is about the introduction of groups and subgroups. And next, closure property of groups and subgroups. The closure property states that for any elements A and B in a group G, their product AB is also in G. Subgroups are closed under the group operation, meaning if A and B are in subgroup, their product is also in the subgroup. Closure is essential for maintaining the group structure and properties. Closure properties of addition of integers. When we add any two integers, the result will always be an integer. For example, 2 plus 3 equals to 5 and 2 minus 3 equals to minus 1. 5 plus 4 equals to 9 and minus 4 plus 6 equals to 2. 7 minus 6 equals to 1 and 6 plus minus into minus 9 equals to minus 3. This is about the example when we had any two integers, and this is about the closure properties of groups and subgroups. And next, associativity property in groups and subgroups. Associativity in groups implies that the grouping of elements in a product does not affect the result. Subgroups inherit the associativity property from the parent group, ensuring that the subgroup operation is well defined. The associative properties allows for the simplification of complex group operations. Associative property, that is A plus B plus C equals to A plus B into B plus C. A into B into C equals to A into B into C. Grouping doesn't matter, and this is about associative properties in groups and subgroups. And identity element in groups and subgroups. Groups have an identity element E such that for any element A in G, A into E equals to E, A equals to A. Subgroups contain the same identity element as the parent group, preserving the identity property with the subgroup. The identity element plays a crucial role in defining the structure of groups and subgroups. This is about the identity element in groups and subgroups. And next, inverse element in groups and subgroups. In a group G, every element has a inverse A inverse minus 1 such that A inverse minus 1 equals to A inverse minus 1 into A equals to E. Subgroups maintain the inverse property, ensuring that each element in the subgroup as an inverse within the subgroup. And inverse allows for the cancellation of elements and the solving of equations within the groups and subgroups. And this is about the inverse element in groups and subgroups. And order of elements in groups and subgroups. The order of an element A in a group G is the smallest positive integer n such that A inverse n equals to E. Subgroups have elements with orders that divide the order of the subgroup following the Lagrange's theorem. Understanding the order of elements is crucial for analyzing the structures and properties of groups and subgroups. Here there is a periodic table of the elements in groups and subgroups you can see. And next, generators and cyclic groups. A group G is a cyclic if it can be generated by a single element A denoted as G equals to A. Subgroups of element groups are also cyclic and can be generated by a subset of the elements that generate the parent group. Generators plays a key role in understanding the structure and properties of cyclic groups and their subgroups. Cyclic group and theorem. G equals to A to the power K belongs to Z, and this is about the generators of cyclic groups and subgroups. And next, normal subgroups and quotient groups. We will going to speak about this normal subgroups and quotient groups. A subgroups H of a group G is normal if for every G in capital G and H in capital H, the conjugative G inverse minus 1 is in H. Normal subgroups allows for the formation of quotient groups G by H, where elements are cosets of H in G under the normality condition. Quotient groups provides insights into the structure and relationships between groups and their normal subgroups. This is about the normal subgroups and the quotient groups. And next, isomorphism and homomorphism in groups and subgroups. An isomorphism is a bijective homomorphism between groups that preserves the group structure and properties. Subgroups related by an isomorphism share similar properties and structures even though they may appear different. Homomorphism map elements and operations between groups and subgroups, highlighting their connections and similarities. And you can see the graph G shown below. And solution for homomorphism and isomorphism. And first we are going to speak about homomorphism. A mapping F from a group G comma O to a group G dash comma 0 O dash is called a homomorphism if F into AOB equals to FA into O dash F into B, where A comma B belongs to capital G and F into A comma F into B belongs to G dash. And then second, isomorphism, a mapping F from a group that is G comma O to a group G dash comma O dash is called a isomorphism if there are three things in isomorphism. First one, F dash is a homomorphism and F is 1 1, and at last third one F is on 2, and this is about the groups and subgroups of isomorphism and homomorphism. And conclusion about this groups and subgroups. Properties of groups and subgroups such as closure, associative identity, and inverses are fundamental for understanding their structures. Subgroups inherit properties from parent groups, allowing further analysis and comparisons of different subgroup structures. The study of groups and subgroups is essential in various mathematical fields, including algebra, number theory, and cryptography. And the multiplication properties, there are four. First one commutative property, second one associative property, and third one identity property, and fourth one zero property. And first one, commutative property, we are going to speak about this property. You can multiply in any order by the commutative property. That is, for example, a into b equals to b into a, and in number we can see that 3 into 4 equals to 4 into 3. You obviously know that 4 into 3 equals to 12. And associative property, second property, associative property, you can group the numbers in any combination. For example, a into b into c equals to a into b into c, and in number 2 into 4 into 5 equals to 2 into 4 into 5. And this is about the associative property. And next, identity property, the product of 1 and any number is called as identity property. For example, a into 1 equals to a, and 6 into 1 equals to, you obviously know, 6. And next, zero property, the last property, the product of 0 and any number is also called as 0, that is called as zero property. That is, a into 0 equals to 0, and the number 9 into 0 equals to 0. This is about the zero properties. And this is the four properties of multiplication properties of groups and subgroups. And thank you everyone for listening my video.